Namaste friends and welcome to this lecture on congruence module n under divisibility in integers. In the last lecture we have learned residue classes module n. Also we have taken some example on residue classes. Here we are going to find all the residue classes modulo 6. We know that there are 6 residue classes modulo 6, namely class of 0, class of 1, class of 2, class of 3, class of 4 and class of 5, because the only possible remainders when any integer is divided by 6 are 0, 1, 2, 3, 4 and 5. That remainders forms the residue classes. Now the class of 0 itself contains 0 and all those integers which are congruent to 0 modulo 6. All the remaining integers congruent to 0 modulo 6 can be obtained by adding multiples of 6 in 0 and subtracting multiples of 6 from 0. When we add multiples of 6 in 0, we will get 0 plus 6 is equal to 6, 6 plus 6 is equal to 12, 12 plus 6 is equal to 18 and so on. When we subtract multiples of 6 from 0, we will get 0 minus 6 is equal to minus 6, minus 6 minus 6 is equal to minus 12, minus 12 minus 6 is equal to minus 18 and so on. Next residue class is class of 1. Itself contains 1 and all those integers which are congruent to 1 modulo 6. Again, all the remaining integers which are congruent to 1 modulo 6 are obtained by adding multiples of 6 in 1 and subtracting multiples of 6 from 1. When we add multiples of 6 in 1, we will get 1 plus 6 is equal to 7, 7 plus 6 is equal to 13, 13 plus 6 is equal to 19 and so on. When we subtract multiples of 6 from 1, we will get 1 minus 6 is equal to minus 5. Minus 5 minus 6 is equal to minus 11. Minus 11 minus 6 is equal to minus 17 and so on. Similarly, the residue class of 2 contains 2 itself and all those integers which are congruent to 2 modulo 6, obtained by adding multiples of 6 into and subtracting multiples of 6 from 2. In this way, we will get 2 plus 6 is equal to 8, 8 plus 6 is equal to 14, 14 plus 6 is equal to 20 and so on. And after subtracting multiples of 6 from 2, we will get 2 minus 6 is equal to minus 4, minus 4 minus 6 is equal to minus 10, minus 10 minus 6 is equal to minus 16 and so on. The residue classes of 3 contains 3 itself and 3 plus 6 is equal to 9. 9 plus 6 is equal to 15, 15 plus 6 is equal to 20 and so on. 3 minus 6 is equal to minus 3, minus 3 minus 6 is equal to minus 9, minus 6 minus 9 minus 6 is equal to minus 50 and so on. The residual class of 4 again contains 4 itself and all the remaining integers which are congruent to 4 modulo 6 can be obtained as 4 plus 6 is equal to 10, plus 6 is equal to 16, plus 6 is equal to 22 and so on. 4 minus 6 is equal to minus 2, minus 2 minus 6 is equal to minus 8, minus 8 minus 6 is equal to minus 14 and so on. The last residue class modulo 6 is class of 5. It contains 5 itself and all the remaining integers which are congruent to 5 modulo 6 are obtained as 5 plus 6 is equal to 11, 11 plus 6 is equal to 17, 17 plus 6 is equal to 23 and so on, and 5 minus 6 is equal to minus 1, minus 1 minus 6 is equal to minus 7, minus 7 minus 6 is equal to minus 13 and so on. In this way we can find the residue classes modulo any positive integer. See, the residue classes modulo 9 are class of 0, class of 1, class of 2, class of 3, class of 4, class of 5, class of 6, class of 7 and class of 8 only. These residue classes covers all integers. You can verify here. Class of 0 contains 0, here is 1, here is 2, 3, 4, 5, again 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and so on. Towards the negative integers, here we have minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, minus 12, minus 11, minus 12 and so on. In this way all the integers are covered in these 6 residue classes. Okay, so there are only 6 residue classes modulo 6, 9 residue classes modulo 9, 8 residue classes modulo 8, and so on. Each integer belongs to exactly one of these residue classes. You have already seen it. For example, 17 is congruent to 5 modulo 6. 17 is congruent to 5 modulo 6. How can we get this? Just divide 17 by 6. When we divide 17 by 6, we get quotient as 2. 6 2s are 12. And when we subtract 12 from 17, we will get the remainder 5. Means 5 is the remainder when 17 is divided by 6. So this 17 is congruent to 5 and 17 belongs to a residue class of 5 modulo 6. 17 belongs to class of 5. Okay. Here minus 3 is congruent to 3 modulo 6. Why? When we divide minus 3 by 6, we will get the remainder 3. But it is somewhere difficult to see how 3 is the remainder when minus 3 is divided by 6. Instead, you can apply the definition of congruence here. We know that A is congruent to B modulo n if and only if n divides A minus B. Here A is minus 3, B is 3, minus 3 minus 3 is minus 6, and it is divisible by 6, and therefore minus 3 is congruent to 3 modulo 6. Means among 0, 1, 2, 3, 4 and 5, only 3 is the integer or remainder which is congruent to minus 3 modulo 6. So here we can say that minus 3 is congruent to 3 modulo 6, and hence minus 3 belongs to the residue class of 3. Minus 3 belongs to class of 3 or residue class of 3. 10 is congruent to 4 modulo 6 because 6 divides 10 minus 4. 10 minus 4 is 6 and 6 is divisible by 6. So 10 is congruent to 4 modulo 6 and hence 10 belongs to class of 4. Again, minus 10 is congruent to 2 modulo 6 because minus 10 minus 2 is minus 12 and minus 12 is divisible by 6. Therefore, minus 10 is congruent to 2 and minus 10 belongs to the residue class of 2 modulo 6. 7 is congruent to 1 modulo 6 because 7 minus 1 is 6 and 6 is divisible by 6. So 7 belongs to class of 1. 12 is congruent to 0 modulo 6 because 12 minus 0 is 12 and it is divisible by 6. So 12 belongs to the residue class of 0 modulo 6. All this is with respect to modulo 6. Thus the residue classes modulo 6 are partitioning the set of all integers. The residue classes modulo 6 means class of 0, class of 1, class of 2, class of 3, class of 4 and class of 5. Partition the set of all integers into disjoint sets. That sets are class of 0 to class of 5. All 6 classes are disjoint, and when we make the union of that 6 residue classes, we will get the whole set of integers, and hence we can say that these residue classes partition the set of all integers into disjoint sets, each containing integers that are congruent to each other modulo 6. Each of the residue class contain those integers which are congruent to each other modulo 6. Okay, means class of 0 contains 0, 6, 12, 18, minus 6, minus 12, minus 18. All these integers are congruent to each other modulo 6. Okay, class of 1 contains 1, 7, 13, 19, minus 5, minus 11, minus 17. All these are congruent to each other modulo 6. Here we are going to learn the theorem there are precisely n distinct residue classes modulo n. With the form of example, we can verify this. Modulo 6, there are only 6 residue classes, not only 6 but exactly 6 residue classes modulo 6, that are class of 0, class of 1, class of 2, class of 3, class of 4 and class of 5. We have to prove this, as there are precisely n distinct residue classes modulo n. You can verify this. This is very easy to verify. This statement can also be written as the set of residue classes modulo n. The set of residue classes modulo n contains only n elements, that are class of 0, class of 1, class of 2 up to class of n minus 1. Like class of 6 residue classes modulo 6 contains only 6 elements, class of 0, class of 1, class of 2 up to class of 5 only. Okay, the set of residue classes modulo 6 contains only 6 elements, that are class of 0, class of 1, class of 2 up to class of 6 minus 1, that is class of 5. Okay, so there is a theorem whose statement is given as the set of residue classes modulo n contains only n elements, that are class of 0, class of 1, class of 2 up to class of n minus 1. Okay, this theorem is given in our syllabus as without proof, so we skip its proof. Now we are going to learn the definition of binary operation on Zn. What is this Zn? This Zn is the set of all residue classes modulo n, which we have seen in the previous slide. Okay, this Zn contains which integers, which elements? Class of 0, class of 1, class of 2 up to class of n minus 1. Okay, a binary operation star on the set of integers modulo n, on the set of integers modulo n. What is the set of integers modulo n? That are class of 0, class of 1, class of 2, class of 3 up to class of n minus 1. The set of integers modulo n is class of 0, class of 1, class of 2 up to class of n minus 1, which is denoted by Zn. And the binary operation star on this Zn, what is it? It is a function. It is a function from Zn cross Zn to Zn that assigns to each ordered pair AB of elements in Zn an element S star B in Zn. Binary operation is operating on 2 elements of Zn, and after operating this star on 2 elements on Zn, we will get a single element of Zn. That is, when star is operating on 2 elements A and B of Zn, we will get the single element S star B in Zn. You can get or understand this concept with the help of examples in the next slide. Addition modulo n and multiplication modulo n, these are two binary operations on Zn. A binary operation addition modulo n on Zn is denoted by plus suffix n. This plus suffix n means this is addition modulo n. Okay, this is addition modulo n, and it can be defined only on Zn, means plus 5 can be defined on Z5 only. It cannot be defined on Z6, Z7 or any other. Plus 5 can be defined only on Z5. Plus 7 can be defined on Z7. Plus 100 can be defined on only Z100. Okay, so a binary operation addition modulo n on Zn is denoted by plus n. And how can you define it? This operation is defined as follows. See, if class of A and class of B are two elements in Zn, if class of A and class of B are any two elements in Zn, after adding these two classes under addition modulo n means plus n, what we get? We will get class of Ax. Where does it belong? This class of X also belongs to Zn. And how can you recognize this X? This X is the remainder when A plus B is divided by n, where class of X belongs to Zn, and it is such that A plus B is congruent to X modulo n, means when we divide A plus B by n, we will get X as a remainder. And such class of X is nothing but class of A plus n class of B. So whenever you have two residue classes in Zn, after adding them, the residue class obtained class of X is such that it is a remainder when A plus B is divided by n. That is, X is the remainder when A plus B is divided by n. Another binary operation on residue class modulo n is multiplication modulo n. It is similar as that of addition modulo n. A binary operation multiplication modulo n is denoted by on Zn is denoted by cross n. This is a sign of multiplication. This n represents, it is defined on Zn, means cross 5 is a multiplication modulo 5. It is only for the set Z5. Okay. Cross 6 is only for Z6 and so on. And this operation is defined as follows. If class of A and class of B are any two classes in Zn, you can multiply them with respect to this cross n. And the multiplication will be the class of X. This class of X also present in Zn, where class of X belongs to Zn. And how is it? It is such that when we actually multiply A and B, that multiplication is congruent to X modulo n. A cross B is congruent to X modulo n. How is it? It means that when we divide A cross B by n, we will get the X as a remainder. Means X is the remainder when A cross B is divided by n. In this way, whenever you have any two residue classes, class of n, class of B in Zn, we can multiply them with respect to cross n by finding the actual remainder X when A cross B is divided by n. And the class of that remainder X is nothing but class of A cross n, class of B. There are some properties of binary operation on Zn, means addition modulo n and multiplication modulo n. First is the closure property. Closure property means whenever we apply addition modulo n or multiplication modulo n on Zn, the resultant is also present in Zn. That is called as the closure property. For any class of A, class of B belongs to Zn, the result of the operation is class of A star class of B, means class of A plus n class of B and class of A cross n class of B, both are the elements of Zn again, is also an element of Zn. Second is the associativity property. Associativity property means when we apply any binary operation on Zn, that means addition modulo n or multiplication modulo n on three elements of Zn, then it is immaterial of order. That means for any class of A, class of B and class of C in Zn, class of A, class of B and class of C in Zn, the operation star satisfies class of A star class of B star with class of C is equal to class of A star with class of B star class of C. Means either you can apply binary operation on a class of A and class of B first and then apply it with class of C, or you can apply that binary operation on class of B and class of C and then you can apply it to class of A. Both results are same or equal. This is called as the associative property. Third is the existence of identity element. There exists an element A belongs to Zn such that for any class of A belongs to Zn, class of A star E is equal to E star class of A is equal to class of A itself. Means there exists element in Zn which we add with any class of Zn modulo n, that residue class remains as it is. Similarly, whenever there exists some element in Zn which we multiply with any residue class of Zn modulo n, that residue class remains as it is. See here. So this E is equal to class of 0, which is the identity element in Zn with respect to the addition plus n. Means whenever we add any residue class of Zn with class of 0, that residue class remains as it is with respect to plus n. Similarly, E is equal to class of 1 is the identity element in Zn with respect to multiplication cross n. Means whenever we multiply any class of Zn with class of 1 with respect to cross n, that residue class in Zn remains as it is. Existence of inverse element. For every class of A belongs to Zn, there exists class of B belongs to Zn such that class of A plus n class of B is equal to class of 0. Means for every class in Zn, every element in Zn, there exists another element in Zn such that whenever we add these two elements with respect to plus n, we will get the 0 element in Zn, which is called as the identity element in Zn with respect to plus n. Okay. Similarly, for every class of Zn, for every class of A in Zn which is other than class of 0, means every non-zero element in Zn, for every non-zero element class of A in Zn, there exists class of B in Zn such that if we multiply these two classes with respect to cross n, we will get the identity element in the multiplication, that means class of 1, such that class of A cross n class of B is equal to class of 1. See, this happens only for the non-zero elements in Zn, only those classes in Zn which are other than class of 0. Okay. See, now we are going to learn very interesting part, that are the addition and multiplication tables in Zn. First of all, we are going to learn the addition table in Z7. We know that Z7 contains the residue classes of class of 0, class of 1, class of 2, class of 3, class of 4, class of 5 and class of 6 only. Means class of 0 to class of 7 minus 1. 7 minus 1 is 6. So it contains only class of 0 to class of 6. 7 elements. So to construct addition table in Z7 which contains 7 elements, we have to construct the table of 8 by 8 rows and 8 columns. This is 8 by 8 table. Now in this table, first of all, you have to write that elements in Z7, class of 0, class of 1, class of 2, class of 3, class of 4, class of 5 and class of 6 in the first row starting from second column in this way. Class of 0, class of 1, class of 2, class of 3, class of 4, class of 5 and class of 6. And we have written this starting from second column. Similarly, we have to write all these elements in the first column starting from second row. That means starting from this in this way. And here in this cell of first row and first column, you have to write the binary operation. Which is the binary operation here we are going to use? That is the plus 7 in this way. Okay. Now we have to actually add the classes. First of all, we are going to add these two classes, class of 0 and class of 0. We know that class of 0 plus class of 0 is class of 0 itself. Class of 0 plus class of 1 is class of 1 itself, because class of 0 is the identity element with respect to plus. When we add this class of 0 to any of these classes remains as it is, and you will get this first row as class of 0, class of 1, class of 2, class of 3, class of 4, class of 5, class of 6 in the similar way. Okay, here we will get class of 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4, 0 plus 5 is 5, 0 plus 6 is 6. Similarly, in the first column, what will happen? We have to add 0 plus 0 as 0, 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, 4 plus 0 is 4, 5 plus 0 is 5 and 6 plus 0 is 6. So this first column is again same as class of 0 to class of 6 in this way. Now we are going to find the value in this cell. This is obtained by adding class of 1 in class of 1. Class of 1 plus class of 1 is class of 2. Class of 1 plus class of 2 is class of 3. Class of 1 plus class of 3 is class of 4. 1 plus 4 is 5. 1 plus 5 is 6. 1 plus 6 is 7, which is not present in Z7. See here, 1 plus 6 will be 7, which is not present in Z7. So what we have to do? You have to find those class in Z7 to which it is congruent. 1 plus 6 is 7. You have to divide that 7 by 7 and find the remainder. 1 plus 6 is 7. When we divide that 7 by 7, we will get the remainder 0. So this addition will be the class of 0. See, how can you get this 0? You have to just add 1 and 6. You will get 7, which is not present in Z7. So you have to divide that 7 by 7 and find the remainder. When we divide 7 by 7, we will get the remainder 0, and so this cell contains class of 0. Similarly, you can get the same values in the remaining cells of this column. Means class of 2 plus class of 1 is nothing but class of 1 plus class of 2. Here we will get 3, here we will get 4, 5, 6 and 0 in this way. Okay. Now you have to find the value in this cell. It will be obtained by adding class of 2 with class of 2. 2 plus 2 is 4. Here 2 plus 3 is 5. Here 2 plus 4 is 6. Here 2 plus 5 is again 7, which is not present in Z7. So you have to divide 7 by 7, you will get the remainder 0. So here we have to write class of 0. Here 2 plus 6 is 8. Again 8 is not present in Z7. So divide 8 by 7, you will get the remainder 1. So here will be the class of 1. All these elements are obtained in this column again, because this addition is commutative. So this row and this column both are same in this way. Okay. Now you have to find the value in this cell. It can be obtained by adding class of 3 with class of 3. 3 plus 3 is 6. So here will be class of 6. 3 plus 4 is 7, which is not present in 7. So you have to divide it by 7. We will get the remainder as 0. Again 3 plus 5 is 8. It is not present in 7. Divided by 7, you will get remainder as 1. So it will be class of 1. 3 plus 6 is 9. 9 is not present in 7 Z7. So divide 9 by 7. You will get remainder as 2. So here will be class of 2. And all these 4 classes are obtained in this column also, and you will get here as class of 6, class of 0, class of 1, class of 2. Again, to find this cell value, you have to add class of 4 with class of 4. 4 plus 4 is 8, not present in Z7. After dividing 8 by 7, you will get 1 as remainder. So here will be the class of 1. 4 plus 5 is 9, which is absent in Z7. So divide 9 by 7, you will get 2 as remainder. So here will be class of 2. 4 plus 6 is 10. 10 is not present in Z7. Divide 10 by 7, you will get the remainder as 3. So here will be class of 3. So the similar classes are obtained in this column also. You will get class of 1, class of 2, class of 3. For this cell value, you have to add class of 5 with class of 5. You will get class of 10, which is not present in Z7. So divide 10 by 7 and you will get the remainder as 3. So here will be class of 3. 5 plus 6 is 11. When we divide 11 by 7, you will get the 4 as remainder. So here will be 4. And the same classes are obtained in this column also. So here will be class of 4. And the last entry remained is obtained by adding class of 6 with class of 6. 6 plus 6 is 12. And when we divide 12 by 7, we will get the 5 as a remainder. So here will be 5, class of 5 as the entry value. In this way, you can find the addition table. See, in this addition table, you get somewhere zeros. See, here is we have 0. Here 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 we have 0. Okay. What is the meaning of these zeros? These 0 means these two zeros are inverses of each other. This 0 means this 6 and this 1. These are inverses of each other. This 0 is obtained due to addition of 5, class of 5 and class of 2. So class of 2 and class of 5 are additive inverses of each other. This 0 is obtained due to addition of class of 4 and class of 3. So class of 4 and class of 3 are additive inverses of each other. In this way, you can get the additive inverses. Okay. Similarly, we can get the multiplication table modulo 7, means multiplication table in Z7. Similar as that of addition table, you have to construct the 8 by 8 table. You have to write the class of 0 to class of 7 in the first row starting from second column as like this. Again, you have to write all these classes in the first column starting from second row in this way. In this cell belonging to first row and first column, you have to write the Sign of binary operation. Here binary operation is multiplication modulo n, so you have to write this here cross 7. Now you have to multiply the corresponding classes and write their result in the cell. Okay, here you can get the entry by multiplying class of 0 with class of 0. Here we can get the entry by multiplying class of 0 with class of 1. We know that when we multiply any of these classes by class of 0, you will get the class of 0 itself. So this first result of row, this first result will be class of 0 only. Okay, so in this row we will get all entries as class of 0. Similarly, in this column, how can we get the results? After by multiplying these classes by 0. So this column also contains all class of zeros. Now here we can get the entry by multiplying this class of 1 by class of 1. Here we can get the entry by multiplying class of 2 by class of 1. Here we can get the entry by multiplying class of 3 by class of 1. But when we multiply any class by class of 1, class of 1 is the identity element with respect to multiplication. So when we multiply any class by class of 1, that class remains as it is. So here we will get class of 1, class of 2, class of 3, class of 4, class of 5 and class of 6 as it is. So we will get the results as like this, class of 1 to class of 6. Similarly, in this column, the results are obtained by multiplying these classes by class of 1. And so these classes remains as it is in this column like this. Okay. Now in this cell, the result is obtained by multiplying class of 2 with class of 2. Class of 2 with class of 2. 2 into 2 is 4. So here will be class of 4. Here 2 into 3 is 6. So class of 6. Here 2 into 4 is 8. But 8, class of 8 is not present in Z7. So you have to divide 8 by 7. You will get the remainder 1. So here will be class of 1. 2 into 5 is 10. Class of 10 is not present in Z7. So divide 10 by 7. You will get 3 as remainder. So here will be class of 3. 2 into 6 is 12. 12 divided by 7. Remainder is 5. Okay. And as the multiplication modulus n is again commutative, all these entries are present in this column also. So we will get here class of 6, class of 1, class of 3 and class of 8. This value is obtained by multiplying class of 3 with class of 3. 3 into 3 is 9, and when we divide 9 by 7 we will get the 2 as the remainder. 3 into 4 is 12. When we divide 12 by 7 the remainder will be 5. 3 into 5 is 15. When we divide 15 by 7 we will get the remainder as 1. 3 into 6 is 18. When we divide 18 by 7 we will get 7 to the 14 and 4 as remainder. Okay, and all these entries are again obtained in this column, and we will get class of 2, class of 5, class of 1 and class of 4. Now here we can get the value by multiplying class of 4 with class of 4. 4 4 is 16, and we divide 16 by 7 we will get the 2 as a remainder. So here will be class of 2. 4 5 is 20. When we divide 20 by 7 the remainder will be 6. 4 into 6 is 24. When we divide 24 by 7 the remainder will be 3. And all these entries are again obtained in this column. You will get class of 2, class of 6, class of 3. These value can be obtained by multiplying class of 5 with class of 5. 5 5 is 25. When we divide 25 by 7 we will get 4 as a remainder. 5 into 6 is 30. When we divide 30 by 7 we will get 2 as remainder. This 2 is also obtained here because here we will get 6 into 5 30. When divide 30 by 7 2 is remainder. And last value is obtained by multiplying 6 by 6. 6 into 6 is 36. When we divide 36 by 7, 1 will be the remainder. 7 5 is 35. 1 is the remainder, and here you will get the class of 1. Now you can observe here every row need not contain class of 1. Every row need not contain class of 1 in the output table. This is the output table. Okay, this is the output table. In this output table, not every row contains 1. We can select where this class of 1 obtained in the output table. See, here we will get 1 class of 1, here we will get class of 1, here we will get class of 1, here we will get class of 1, here we have obtained class of 1, and here we have obtained class of 1. Okay, this class of 1 means it is obtained by multiplying 1 with 1. So these two classes are multiplicative inverses of each other. This class of 1 is obtained by multiplying class of 4 with class of 2. So class of 2 and class of 4 are multiplicative inverses of each other, modulo 7. Okay, this class of 1 is obtained by multiplying class of 5 with class of 3. So class of 3 and class of 5 are multiplicative inverses of each other, modulo 7. Again here we will get 4 and 2 are the multiplicative inverses of each other, modulo 7. Here 1 is obtained due to multiplication of 3 and 5. So again we will get the result that 3 and 5 are the multiplicative inverses of each other, modulo 7. Here 1 is obtained due to the multiplication of 6 with itself. So 6 is multiplicative inverse of itself, modulo 7. Okay, 6 is multiplicative inverse of itself, modulo 7. In this way you will get the multiplicative inverses from the multiplication table as like additive inverses in the addition table. Okay. Next is the Fermat's little theorem. What does it says? Statement is, let P be a prime and A be an integer not divisible by P. A is not divisible by P means A is not a multiple of P. A cannot be 0, P, 2P, 3P, 4P, etc. or minus P, minus 2P, minus 3P, minus 4P, etc. In this way, A is integer not divisible by P. Then A raised to P minus 1 is congruent to 1 modulo P. See what is Fermat's little theorem? Let P be a prime and A is any integer which is not divisible by P. Then A raised to P minus 1 is congruent to 1 modulo P. So how can you prove it? Consider the set of multiples of A with the integers from 1 to P minus 1. See here, A into 1 is A into 2 is 2A, A into 3 is 3A, up to A into P minus 1 is P minus 1 times A. Here we have considered the multiples of 1, 2, 3 up to P minus 1 with A. Okay, what do you get? Here A is not divisible by P. That is hypothesis for this theorem. That is given thing in this theorem. A is not divisible by P. And 1, 2, 3 up to P minus 1, none of them is also divisible by P. Okay, A is not divisible by P. 1, 2, 3 up to P minus 1, these are also not divisible by P. Therefore, none of these elements in the set is divisible by P. And P is a prime. And P is a prime. So what we can say? All these elements in the set are relatively prime to P. Means their GCD of every element in this set with P is 1. GCD of every element in this set with P is 1. So none of these elements are congruent to each other modulo P. Because A is not divisible by P, by cancellation law, if two elements if two elements are congruent to each other modulo p, the GCD of A and P is 1, you can cancel A and you will get 1 is congruent to 3, 1 is congruent to 4, 4 is congruent to 5, like this, which is not true. So none of these elements are congruent to each other modulo P, because here we have mentioned the reason. What is the reason? Suppose Ka is congruent to Ma modulo P. Suppose there are two elements in this set, namely Ka and Ma, which are congruent to each other modulo P. K is congruent to Ma modulo P, where A is not divisible by P, where P is prime. Therefore, the GCD of A and P is 1. And hence, you can apply here cancellation law. After applying cancellation law, A will be get cancelled and you will get K is congruent to M modulo P. But none of the multiples here, the multiples of A are 1, 2, 3 up to P minus 1. None of two of these are congruent to each other modulo P, and so this cannot be true. You can give this reason in other way. Suppose K is congruent to M modulo P for some 1 less equal Km less equal P minus 1, means K and M are among 1 to P minus 1. Then what we can say? K minus Km is congruent to 0 modulo P, or you can say P divides K minus Km. Okay, means P divides A times K minus M. But P does not divide A and P is a prime, so P must divides K minus M. Okay, P cannot divide A, so P must divide K minus M. But K and M both are less than P and greater than 0. So it divides K minus M. If and only K minus M itself is a 0. Okay, K minus M is 0. K minus M is 0 means K is equal to M. Okay, in this way. So K is congruent to MA if and only K and M are same. Means the elements A, 2A, 3 up to P minus 1 times A, all these are distinct elements under the congruence modulo P. So let us take the product of all elements in this set as like A into 2A into 3A into dot dot into P minus 1 times A. Okay, so what do we get? These are congruent to 1, 2, 3 up to P minus 1 in any other order. Means A will be congruent to 2, 2A will be congruent to 3, 3A will be congruent to 5, 4A will be congruent to 1. In this way, these all P minus 1 elements are distinct congruent modulo P. Means exactly one of them is congruent to 1 modulo P, exactly one of them is congruent to 2 modulo P, exactly one of them is congruent to 3 modulo P, exactly one of them is congruent to 4 modulo P, and so on. The remaining will be the congruent to P minus 1 modulo P. So the product of these elements under the congruence modulo P is congruent to 1, 2, 3 up to P minus 1. Okay. Now in this multiplication A into 2A into 3 into dot dot into P minus 1 times A, you can collect the A's together. The remaining will be the product of 1 into 2 into 3 into P minus 1 as like this. Okay, so we'll get A into A into A into A. How many times? P minus 1 times. It will result as A raised to P minus 1. It will be A raised to P minus 1. This is not A raised to P, this is A raised to P minus 1. Into what? 1 into 2 into 3 into P minus 1 is congruent to 1 into 3 into up to P minus 1. These product cancels each other due to cancellation law, because the GCD of this product mode with P is 1. So it results as this is a raised to p minus 1, not a raised to p. This is a raised to p minus 1 times p minus 1 factorial is congruent to p minus 1 factorial modulo p. But p minus 1 factorial is relatively prime to p. So by cancellation law, you can cancel it and you will get a raised to p minus 1 congruent to 1 modulo p. Because on the right side here is only p minus 1 factorial, and after cancelling it, you will get 1. So in this way, we proved here Fermat's little theorem as if p is a prime and a is not divisible by p, then a raised to p minus 1 is congruent to 1 modulo p. There is a corollary. Let p be a prime and a be any integer, then a raised to p is congruent to a modulo p. This corollary is based on Fermat's little theorem. In the Fermat's little theorem, there is also p as a prime, and if a is not divisible by p, then there was a raised to p minus 1 is congruent to 1 modulo p. Here a is any integer and we want to show that a raised to p is congruent to a modulo p. So what will be the proof? Here we have considering two cases. First case is if p divides a. If p divides a, then a is divisible by p. So a is congruent to 0 modulo p. Okay. So when p divides a, p is also divides any power of a. If p divides a square also, p divides a cube also. In this way, p divides a raised to p also. Now p divides a and p divides a raised to p. Therefore, p divides a raised to p minus a. Okay. In this way, as p divides a raised to p minus a, by the definition of congruence, a raised to p becomes congruent to a modulo p. Okay. So this is very easy in this case when p divides a. Suppose we have the second case, p does not divide a. Now p is a prime and p does not divide a means a is not divisible by p. Then you can apply here the Fermat's little theorem. By Fermat's little theorem, we get a raised to p minus 1 is congruent to 1 modulo p. Now you have to just multiply both sides by a by the properties of congruence relation. In this way, what we get? A raised to p minus 1 multiplied by a congruent to 1 multiplied by a modulo p. A raised to p minus 1 times a is a raised to p, and 1 times a is a itself. So you get a raised to p congruent to a modulo. So in any case, if p is a prime, a raised to p is congruent to a modulo p for any integer a. Next is Euler's phi function. This Euler's phi function is defined on the set of positive integers. Means you can find the value of phi of n for every positive integer n. How it defines here. Euler's phi function denoted by phi of n is defined as the number of positive integers. What is this? This phi of n is the number of positive integers satisfying certain condition. What is the certain condition? That positive integers are either less than or equal to n and that are co-prime to n. So what is phi of n? Phi of n is the number of positive integers which are either less than or equal to n, but they are co-prime to n. Co-prime to n means their GCD with n is 1. Any two integers are said to be co-prime if their GCD is 1. So here we have to just count the positive integers which are less than or equal to n and relatively prime to n or co-prime to n, or whose GCD with n is 1. Two numbers are said to be co-prime if their greatest common divisor means GCD is 1. So here we have to just count the number of positive integers less than or equal to n whose GCD with n is 1. Means we have to just count those positive integers less than or equal to n which have no any factor in common with n other than 1. Okay. Formally, phi of n, what is it? It is equal to set count of, cardinality of. This mod denotes the cardinality or count of set, number of elements in the set of. What is the set? Set is set of positive integers k. Set of positive integers k. How it will be less than or equal to n, means it is greater than or equal to 1 because it is positive integer, and it is less than or equal to n. And what is the next condition? It is co-prime to n, means its GCD with n is 1 and GCD of k and n is 1. So phi of n is the count or cardinality of set of those positive integers k which are greater equal to 1 and less equal to n and whose GCD with n is 1. Example, calculate phi of 1. There is only one positive integer which is less than or equal to 1, that is 1 itself, and the GCD of 1 with 1 is 1. So what we get? We have phi of n is equal to set of those is equal to the count of set of integers k which are greater equal 1 and less equal n whose GCD with n is 1. Similarly, we can find the phi of 1 as set count of set of those positive integers k which are greater equal 1 and less equal 1 whose GCD with 1 is 1. Now the only integer which is greater equal and less equal 1 is 1 itself, and it is the only positive integer whose GCD with 1 is 1. So this set contains only a single element, that is 1. Okay, and so the cardinality of this set or count of this set is only 1, and so phi of 1 is 1. Next, calculate phi of 2, phi of 3, phi of 4. Similarly, you can find this Euler's phi function for 2, 3, 4. See, how can we get phi of 2? Phi of 2 is equal to set of those positive integers k which are greater equal 1 and less equal to whose GCD with 2 is 1. You have to take the count of this set as phi of 2. Now, the only positive integers which are greater equal 1 and less equal to are 1 and 2 itself. Only 1 and 2 are the integers which are greater equal 1 and less equal to. And the GCD of 1 with 2 is 1. But GCD of 2 with 2 is 2, not equal to 1. Means the only positive integer satisfying this condition is k is equal to 1. So this set contains only one element, that is 1. Okay, in this way there are only two integers which are greater equal to 1 and less equal to, that are 1 and 2, but GCD of 2 with 2 is 2, not equal to 1. So that 2 cannot satisfy this condition, only 1 can satisfy the condition, and so this set contains only single element 1, and so phi of 2 is 1. Now to find phi of 3, how can we get? Phi of 3 is equal to again set of those integers which are greater equal 1 and less equal 3 and whose GCD with 3 is 1. Now the only positive integers greater equal 1 and less equal 3 are 1, 2 and 3. GCD of 1 with 3 is 1. GCD of 2 with 3 is 1. But GCD of 3 with 3 is 3, which is not equal to 1. So the only two integers 1 and 2 satisfies this condition, and so phi of 3 will be the count of set containing only two elements 1 and 2. 1 and 2 are the only two positive integers which are less than or equal to 3 and whose GCD with 3 is 1. So this count is 2 and phi of 3 is 2. Phi of 4. To find phi of 4, again we have to find the positive integers which are less equal 4, that are 1, 2, 3 and 4. 1, 2, 3 and 4 are the positive integers which are less than or equal to 4. Among them, GCD of 1 with 4 is 1, GCD of 3 with 4 is 1, but GCD of 2 with 4 is 2 and GCD of 4 with 4 is 4. So the only two integers 1 and 3 satisfies the condition. So phi of 4 will be the count or cardinality of set containing only two elements 1 and 3, and so phi of 4 is equal to 2. Okay. Next example, calculate phi of 5, phi of 8 and phi of 12. Here again phi of 5 can be obtained by same manner. The positive integers less than or equal to 5 are 1, 2, 3, 4 and 5. Among them, GCD of 5 with 5 is 5, which is not equal to 1. But GCD of 1, 2, 3, 4 with 5. GCD of each of 1, 2, 3, 4 with 5 is 1. Means 1, 2, 3 and 4. All these 4 positive integers are co-prime with 5. Therefore, phi of 5 will be the cardinality of set containing 1, 2, 3, 4. Contains 4 elements, therefore phi of 5 is 4. To find phi of 8, again there are 8 positive integers less than or equal to 8, namely 1, 2, 3, 4, 5, 6, 7, 8. Among them, 2, 4, 6 and 8 are not co-prime with 8. Okay, 2, 4, 6 and 8 are not co-prime with 8. The only integers co-prime with 8 are 1, 3, 5 and 7. 1, 3, 5 and 7. Therefore, it is equal to cardinality of set containing elements 1, 3, 5, 7, which are 4 in number, and therefore phi of it is equal to 4. Now phi of 12. To find phi of 12, again there are 12 positive integers 1 to 12 less than or equal to 12. Among them, 2, 3, 4, 6, 8, 9, 10, 12 are not co-prime to 12. Only the positive integers co-prime to 12 are 1, 5, 7 and 11. Again these are 4 in number, so phi of 12 is 4. In this way you can find the Euler phi function for any positive integer. Properties of Euler's phi function. What are the properties? If P is a prime, very nice property. If P is a prime, phi of P is just P minus 1. Means we know that 2 is a prime, phi of 2 is 2 minus 1 is 1. 3 is a prime, phi of 3 is 3 minus 1 is equal to 2. 5 is a prime, so phi of 5 is equal to 5 minus 4, it is equal to 4. 11 is a prime, so phi of 11 will be 11 minus 1 is equal to 10. This is very nice property for Euler's phi function. Next property, P is a prime number and K is a positive integer, then phi of P raised to K is equal to P raised to K minus P raised to K minus 1. This is again very nice formula to get the Euler's phi function of prime raised to any positive integer. By using this formula, you can find the Euler's phi function of any positive power of any prime number. And this also can be written as P raised to K minus 1 times P minus 1. When you take common P raised to K minus 1 from these two terms, you will get P raised to K minus 1 into P minus 1. See, if you are to find the phi of 25, how you can find phi of 25? 25 is 5 square. 25 is nothing but 5 square. So, how can we get it? P is 5, K is 2. So, here will be 5 raised to 2 minus 1. That means 5 raised to 1. That is 5 into bracket 5 minus 1. 5 minus 1 is 4. 5 into 5, 4 is 20. In this way, you can get phi of 25 is equal to 20 in just few seconds. Okay. So, this is very good formula for us. Third property is for two positive integers m and n that are co-prime, means they have no positive integer as a factor in common other than 1. Means m and n have only one factor in common, that is plus 1 and minus 1. Okay, here we are thinking about only positive integers, so m and n have only one positive integer as a factor in common, that is 1, because they are co-prime. Then what happened? Phi of m into n is equal to phi of m into phi of n. This is again very nice formula. Suppose you have to find phi of 12. That 12 can be written as 3 into 4. And 3 and 4 are co-prime. So that phi of 12 can be written as phi of 3 into 4 is equal to phi of 3 into phi of 4. Very good. That phi of 3 is, as 3 is prime, phi of 3 becomes 3 minus 1, that is 2. So this phi of 3 becomes 2. And this phi of 4, this 4 can be written as 2 square, like this, prime raised to positive integer, 2 square. Phi of 4 will be 2 square. And how we will get? Its value will be 2 raised to 2 minus 1 into bracket 2 minus 1. 2 minus 1 is 1. Here 2 minus 1 is 1. 2 raised to 1 is 2. 2 into 1 is 2. In this way, this will be 2. This will be 2. 2 into 2 will be 4. In this way, you can find the Euler's phi function of any positive integer quickly. Again, there is another property of Euler's phi function. For any positive integer n having canonical form, n is equal to p1 raised to k1 into p2 raised to k2 into dot 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 into pr raised to kr. This is a canonical form of n, which is written as a product of powers of distinct primes. p1, p2, pr are distinct primes, and n is written as a product of powers of these distinct primes. In this case, phi of n is obtained as product of pi minus 1 into pi raised to ki minus 1, where I is from 1 to r. Means, how can you get this? p1 raised to k1 minus 1 into bracket p1 minus 1 into p2 raised to k2 minus 1 into bracket p2 minus 1. Like this. Phi of p raised to k is what? P raised to k minus 1 into bracket p minus 1. Like this. Here phi of n will be p1 raised to k1 minus 1. You have to just make this index by less by 1. Means p1 raised to k1 minus 1. Make this index less by 1. p1 raised to k1 minus 1 and multiply it with p1 minus 1. Again multiply it with p2 raised to k2 minus 1 and multiply it with the p2 minus 1 up to pr raised to kr minus 1 and multiplying it with pr minus 1. Euler's theorem statement is, let n be a positive integer and a is any integer such that GCD of n is 1. Means a is co-prime to n. A is relatively prime to n. They have no any positive integer as a factor common other than 1. Okay, n is a positive integer and a is integer which is relatively prime to n. GCD of n is 1. Then a raised to phi of n, a raised to phi of this positive integer n is congruent to 1 modulo n. Okay, how can we get this? Like Fermat's little theorem, you have to again find the multiples of a, like this. If n is equal to 1, what do you get? Phi of 1 is 1. If n is equal to 1, phi of n means phi of 1, it is equal to 1. So it becomes a raised to phi of 1, means a raised to 1. Phi of n is equal to phi of 1 is equal to 1. So it will be a raised to phi of n means a raised to 1, and a raised to 1 is a. And here a is 1. Okay, n is 1 and every integer is divisible by 1. So every integer is congruent to 0 modulo 1. So a is also congruent to 0 modulo 1. But 1 is also congruent to 0 modulo 1. In this way, you can say that indirectly this a is congruent to 1 modulo 1. And indirectly this a raised to phi of n is congruent to 1 modulo 1. So you have to consider here the case that n is greater than 1. Because if n is equal to 1, this holds trivially. So you have to consider the case n is greater than 1. Let a1, a2 up to a suffix pi n. These are the positive integers less than n which are relatively prime to n. Okay. We know that phi of n are the phi of n is the number of positive integers which are less than or equal to n and relatively prime to n or co-prime to n. Just denote that positive integers which are less than or equal to n and relatively prime to n by this way: a suffix 1, a suffix 2 up to a suffix phi of n. These are how many in number? Phi of n in number, first, second up to phi of nth element. So these elements are phi of n in number, and these are positive integers less than or equal to n which are relatively prime to n. Okay. As n is greater than 1, none of them is equal to n, so we can say these are strictly less than n and relatively prime to n. These are strictly less than n and relatively prime to n. Because GCD of n is equal to 1. It follows from the cancellation law that, so multiply all these, like Fermat's little theorem, you have to multiply all these elements a1, a2, a5n by a, and none of two of them will be congruent to each other. Okay, because if two of them are congruent to each other, by cancellation law a will be get cancelled and you get one of a1 to a5n is congruent to another modulo n, which is impossible. Okay, so by cancellation law it follows that these are congruent to a1, a2, a5n in some order, not necessarily in the orders of appearance. Means it is not necessary that a into a1 is congruent to a1, a into a2 is congruent to a2, a into a3 is congruent to a3, but a into a1 must be congruent to exactly one of these. A into a2 must be congruent to exactly one of these in this way. Okay, so what you can say, if we multiply this multiplication will be congruent to multiplication of this modulo n. Hence a into a1 into a2 into dot 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 into a phi n is congruent to a1 into a2 into a phi n modulo n. Okay, again here we get a into a phi n times, though it will be a raised to phi of n, and what is the remaining? a1 into a2 into up to a phi n, that will be cancelled with this a1 into a2 into a phi n on the right side. So on the right side there will be just 1, and on the left side there will be a into a phi n times. In this way the left side becomes a raised to phi n and right side will be 1, and we proved the Euler's theorem as a raised to phi n congruent to 1 modulo n in both the cases. Examples. First example is prove that 3 raised to 256 is congruent to 21 modulo 100. This is very bigger number, so you cannot get this by trial and error, means by taking 3 raised to 256 in the actual manner. You cannot get this value. Okay, so what we have to do, we have to use some properties and theorem. Okay, first of all you have to find phi of 100, because Euler's theorem says that if n is a positive integer and a is congruent to n, then a raised to phi of n is congruent to 1 modulo n. Here 3 is congruent, 3 is co-prime to 100. GCD of 3 and 100 is 1. So you can use here Euler's theorem. Okay, here you can use the Euler's theorem. As the GCD of 3 and 100 is 1, you can use here Euler's theorem. And for Euler's theorem you want phi of n means phi of 100. So first of all you have to find the phi of 100. Solution. We have GCD of 3 and 100 is 1. So by Euler's theorem we get 3 raised to 500 is congruent to 1 modulo 100. Now our target to find 500. To find 500, you have to first of all write 100 in the canonical form. Means product of powers of distinct primes. This 100 is 25 into 4. 25 4 is 100. 25 can be written as 5 square, 4 can be written as 2 square. So 500 can be written as 5 of 2 square into 5 square, where 2 and 5 both are prime. So how can we get this here? Just make this index less by 1 and multiply it by 2 minus 1. Just make this index less by 1 and multiply it by 5 minus 1. You will get 2 raised to 2 minus, here initially index is 2. By making it less by 1 you will get 2 raised to 1. So 2 into 2 minus 1 into, again here initially we have index 2. Making it less by 1 it will be 1. So 5 raised to 1 is 5 into 5 minus 1. So it will be 2 into 1 into 5 into 4. 2 into 5 into 4 it will be 40. 2 into 5 is 10. 10 into 4 is 40. 40 into 1 is 40. So 500 is 40. So what you get here? Here we get 3 raised to 40 is congruent to 1 modulo 100. 3 raised to 40. 40 is congruent to 1 modulo 100. But we want 256. So you have to go nearer to this 256. Okay. So to get nearer to 256 from 40, you have to divide this 246 by 40 with division algorithm. So what do you get? By division algorithm we have 256 is equal to 40 into 6, 240. 240 plus 16 is 256. So you can apply division algorithm here and you will get 256 is equal to 40 into 6 plus 16. Therefore this 3 raised to 256 can be written as 3 raised to 40 into 6 plus 16. Okay. This index is the addition of two numbers. One number is 40 into 6 and another is 16. We know that a raised to m plus n is a raised to m into a raised to n. Likewise, it will be 3 raised to 40 into 6 into 3 raised to 16. Okay. This 3 raised to 40 into 6 can be written as 3 raised to 40 whole raised to 6. So it will be 3 raised to 40 raised to 6 into 3 raised to 16. But here 3 raised to 40 is congruent to 1 modulo 100. So this whole thing can be congruent to 1 raised to 6 into 3 raised to 16 modulo 100. Congruent to 1 raised to 6 into 3 raised to 16 modulo 100. But 1 raised to 6 is again 1. 1 into 3 raised to 16 is 3 raised to 16. So indirectly it is congruent to 3 raised to 16 modulo 100. Okay. Now this 3 raised to 16 also can be written as 3 raised to 4 whole raised to 4. 4 into 4 is 16. Okay. So it can be written as 3 raised to 4 raised to 4. Where this 3 raised to 4 is 3 into 3 is 9. 9 into 3 is 27. 27 into 3 is 81. So it will be 81 and it can be written as congruent to 81 raised to 4. How can we reduce this number 81? Modulo 100. See, 81 plus 19 is 100. 81 plus 19 is 100. So you can say that 81 is congruent to minus 19 modulo 100. 81 plus 19 is 100. So 81 is congruent to minus 19 modulo 100. So you can write here congruent to minus 19 raised to 4 modulo 100. Now this minus 19 raised to 4 can be written as minus 19 square raised to square. Okay, minus 19 raised to 2 raised to 2. The square of minus 19 is 361. So it will be 3 raised to 361 bracket square. Okay, modulo 100. Here 361 is congruent to 61 modulo 100 because when we divide 361 by 100, you will get the remainder as 61. So it will be 61 square modulo 100. Now you have to make the square of 61. Very easy to find the square of any positive integer. So to get the square of 61, what you have to do? Write the square of 1 at the unit place, that is 1. You have to double the multiplication of these two elements, means 6 into 2 is 6 into 1 is 6, and double it, you will get 12. So you have to write 2. Then 1 will be carry and add it into the square of 6. Square of 6 is 36. 36 plus 1 is 37. In this we can get the square of 61. How you can get it? Write the square of 1 is equal to 1 at the unit place. If it is in 2 digit, write the unit place of that digit and keep remaining as a carry. Square of 1 is 1, so write it as unit in the unit place. Make the product of these two and make its double again. 6 into 1 is 6, its double will be 12. 12 is 2 digit number, so write unit place of 12 as 2 here, 1 as a carry. Keep 1 as a carry. Now make the square of 6, 36, and add it into that carry, that is 37. The process is stopped, and in this way you will get that 3 raised to 256 is congruent to 3721 modulo 100. And when we divide these by 100, you will get the 21 as a remainder. So indirectly 3 raised to 256 is congruent to 21 modulo 100. This is proved. Second example. Prove that 10 factorial is congruent to minus 1 modulo 11. First of all, keep in mind what is factorial. What is 10 factorial? 10 factorial is a product of 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay. So you have to think about each of that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 modulo 11. We have 1 is congruent to 1 modulo 11. Okay. Means when we divide 1 by 11, you will get 1 as it is. 1 as a remainder. Okay. When we divide 1 by 11, we will get 1 as a remainder. When we divide 10 by 11, we get 10 as a remainder. It's okay. But you have to make this 10 smaller modulo 11. So to make it smaller, what you can write here? We know that 10 plus 1 is 11, which is divisible by 11. 10 plus 1 is 11, which is divisible by 11. So 10 is congruent to minus 1 modulo 11. Okay, because 10 minus 1 is 10 plus 1, 11, which is divisible by 11. So we can say that 10 is congruent to minus 1 modulo 11. Similarly, 2 is congruent to 2 modulo 11. And 9 is congruent to minus 2 modulo 11, because 9 minus minus 2 is 11, which is divisible by 11. Okay. Then 3 is congruent to 3 modulo 11. And 8 is congruent to minus 3 modulo 11, because 8 minus minus 3 is 8 plus 3, and it is equal to 11. 4 is congruent to 4 modulo 11. In this way, 7 is also congruent to minus 4 modulo 11, because 7 minus minus 4 is 7 plus 4, that is 11. 5 is congruent to 5 modulo 11. In this way, 6 is congruent to minus 5 modulo 11, because 6 minus minus 5 is 6 plus 5, that is 11, which is a multiple of 11. Okay, in this we get the congruence value of every integer from 1 to 10 modulo 11. Now 10 factorial is multiplication of all these integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So indirectly it will be the multiplication of 1, 2, 3, 4, 5 into minus 5, minus 4, minus 3, minus 2, minus 1 modulo 11. In this way, therefore 10 factorial is equal to 1 into 2 into 3 into 4 into 5 into 6 into 7 into 9 into 10, congruent to Now you have to write these elements on right side. You will get congruent to 1 into 2 into 3 into 5, 4 into 5 into minus 5 into minus 4 into minus 3 into minus 2 into minus 1 modulo 11. Here 5 negative signs. Multiplication of odd number of negative signs is negative. Therefore, this product of 5 negative signs will be negative, and you will get minus 1 into 1 is 1, 2 into 2 is 4, 3 into 3 is 9, 4 into 4 is 16, 5 into 5 is 25 modulo 11. Here, when we divide 25 by 11, we will get 3 as a remainder. When we divide 16 by 11, we will get 5 as a remainder. So, this looks like minus 1 into 4 into, again see, 9 minus minus 2. 9 minus minus 2 is 9 plus 2. 9 plus 2 is 11, which is divisible by 11. So you can say 9 is congruent to minus 2. You keep 4 as it is, minus 1 as it is. Instead of 9, we have written minus 2 because 9 minus minus 2 is 11, which is multiple of 11. So 9 can be considered as congruent to minus 2 modulo 11. 16 is congruent to 5 because 16 minus 5 is 11, which is divisible by 11. So you can minimize this 16 in evaluation as 5 congruent modulo 11. 16 is congruent to 5 modulo 11. Again 25 minus 3 is 22. 22 is a multiple of 11, or 22 is divisible by 11. So instead of 25 you can write here congruent to 3 modulo 11. Now here are two negative signs. Negative into negative becomes positive. So just it is congruent to 1 into 4 into 2 into 5 into 3. 1 into 4 is 4, 4 into 2 is 8, 8 into 5 is 40, into 3 is 120 modulo 11. And 120 is congruent to minus 1 modulo 11 because 120 minus minus 1 is 120 plus 1, that is 121, which is square of 11. Okay, which is square of 11 means it is divisible by 11. 120 minus minus 1 is 121, which is divisible by 11. Therefore 120 is congruent to minus 1 modulo 11. In this way, this 10 factorial becomes congruent to minus 1 modulo 11. Next example, prove that 7 divides 2222 raised to 5555 plus 5555 raised to 2222. This is very big number, but you can get the solution by using the Euler-Phi function and properties of congruence. Solution: 7 is a prime. 7 is a prime. Therefore, by Fermat's little theorem, we get 2222 raised to p minus 1 is congruent to 1 modulo p. 2222 raised to p minus 1 is congruent to 1 modulo p. Here p is 7, so p minus 1 is 6. So by using Fermat's little theorem, we will get 2222 raised to 6 is congruent to 1 modulo 7. Likewise, we get 5555 raised to 6 is congruent to 1 modulo 7. Again, by division algorithm, when we divide this 5555 by 7, we get 5555 is equal to 6 into 925, and 5 will be the remainder. Okay. Similarly, by dividing 2222 by 7 by 6, 2222 by 6, we will get 2222 is equal to 6 into 370 plus 2. Now you have to write this 2222 raised to 5555 as 2222 raised to, instead of 5555 you can write here there as 6 into 925 plus 5. Similarly, instead of 2222 as the index here, you can write this 6 into 370 plus 2. So what you get? Again, we have applied the division algorithm here for 5555 divided by 7. Quotient will be 793 and 4 will be the remainder. You can easily divide it. Similarly, 2222 can be written as 7 into 317 plus 3 as the remainder. Therefore, what we get? 2222 raised to 5555 is equal to 2222 is raised to 6 into 925 plus 5. Okay. Now, this can be written as 2222 raised to 6 raised to 925 into 2222 raised to 5. A raised to m plus n is equal to a raised to m into a raised to n. So it will be 2222 raised to 6 raised to 925 into 2222 raised to 5. This is congruent to 1 modulo 7. So it will be 1 raised to 925. It becomes very less. Now you have to think about only 2222 raised to 5. Okay. So how can get here 3 raised to 5? Since 2222 is equal to 7 into 370 plus 3, this is congruent to 3 modulo 7. 2222 is congruent to 3 modulo 7. So this can be replaced as congruent to 3 raised to 5 modulo 7. This 1 raised to 925 is 1 and 3 raised to 5 is 243 modulo 7. Now 1 into 243 is 243 modulo 7. You have to divide this by 7 and find the remainder. 7 3s are 21. You will get 33 here, and 7 4s are 28. 5 will be the remainder. So indirectly you will get this as 243, which is congruent to 5 modulo 7. Okay, so what we get? 2222 raised to 5555 is congruent to 5 modulo 7, denoted by 1. Now we have to think about 5555 raised to 2222. That 2222 can be written as 6 into 370 plus 2. Now again, likewise this you can write it as 5555 raised to 6 raised to 370 plus 5555 raised to 2. This is congruent to 1 modulo 7, so it can be replaced as congruent to 1 raised to 370 into, here we have already applied the division algorithm. By applying this, you can say that this is congruent to 4 modulo 7. So it becomes 1 raised to 370 into 4 square modulo 7. 1 raised to 370 is 1 into 4 square is 16. So it will be 1 into 16. 16 congruent to 16 modulo 7, and when we divide 16 by 7, it will be 2. 7 2s are 14. 2 will be the remainder of this. It will be congruent to 2 modulo 7. In this way, we can say 5555 raised to 2222 is congruent to 2 modulo 7. Okay. Hence, from first and second, what is first? First was 2222 raised to 5555 is congruent to 5 modulo 7, and second is 5555 raised to 2222 is congruent to 2 modulo 7. In this way, we will get the addition is congruent to 5 plus 2 modulo 7. 5 plus 2 is 7. So it is congruent to 7 modulo 7. But 7 is congruent to 0 modulo 7. Because when we divide 7 by 7, we will get the remainder as 0. So in this way, we can say that 2222 raised to 5555 plus 5555 raised to 2225 is congruent to 0 modulo 7. Means when we divide this number by 7, we will get the 0 as the remainder. In this way, we can say that 7 divides this number. This shows that 7 divides 2222 raised to 5555 plus 5555 raised to 2222. Next example, prove that 89 divides 2 raised to 44 minus 1. Just you have to find the congruence of powers of 2 modulo 89, because here the power of 2 is less than the phi of 89. 89 is a prime number, so its Euler's phi function is 88. Here we have given the index of 2 as less than 88, so directly start from 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4 and so on modulo 89. So what do you get? We have 2 is congruent to 2 modulo 89. Because it is less than 89, you have to write this positive integer congruent to itself modulo 89. Still it is less than 89. 2 raised to 2 is 4 congruent to 4 modulo 89. 2 raised to 3 is 8 congruent to 8 modulo 89. 2 raised to 4 is 16 congruent to 16 modulo 89. 2 raised to 5 is 32 congruent to 32 modulo 89. 2 raised to 6 is 64 congruent to 64 modulo 89. 2 raised to 7 is 128, which is congruent to 128 modulo 89. Here 120 is greater than 89, so divided by 89 means just subtract 89 from 128, you will get 39. Okay, 39. So 128 is congruent to 39 modulo 89, so it will be congruent to 39 modulo 89. Now 2 raised to 8, how can we get 2 raised to 8 from 2 raised to 7? Just multiply 2 raised to 7 by 2, you will get 2 raised to 8. So 2 raised to 8 will be congruent to 2 raised to 7 into 2, but 2 raised to 7 is congruent to 39. So 2 raised to 8 will be congruent to 2 into 39, like this. 2 raised to 8 is congruent to 2 into 2 raised to 7 modulo 89. So 2 raised to 8 is congruent to 2 into that 2 raised to 7 can be replaced as congruent to 39 modulo 89. 39 into 2 is 78, and it is again less than 89. So keep 78 as it is. Now 2 raised to 9. 2 raised to 9 is what? It is 2 into 2 raised to 8, but 2 raised to 8 is congruent to 78. So you can replace this as congruent to 78 modulo 89. 78 into 2. 78 into 2 is 156, so it will be congruent to 156 modulo 89. Now 156 is beyond 89, greater than 89. So you have to subtract 89 from 156 and you will get 67. So it will be congruent to 67 modulo 89. Okay. Now go towards 200, 2 raised to 10. 2 raised to 10 is 2 into 2 raised to 9. 2 raised to 9 is congruent to 67. So it will be congruent to 2 into 67 modulo 89. 2 into 67 is 134. Okay, so it will be congruent to 134 modulo 89. Again it is greater than 89, so subtract 89 from 134, you get 45. So 2 raised to 10 is congruent to 45 modulo 89. So 2 raised to 11 is 2 into 45 modulo 89, it will be 90, and 90 is greater than 89, so subtract 89 from 90, you will get 1. So 211 is congruent to 1 modulo 89. 211, 2 raised to 11 is congruent to 1 modulo 89. This 44 can be written as a multiple of 11. So it will be 11 into 4. So it can be written as 2 raised to 11 raised to 4. And this 2 raised to 11 is congruent to 1 modulo 89. So it will be congruent to 1 raised to 4 modulo 89. 1 raised to 4 is 1. So indirectly it is congruent to 1 modulo 89. And hence we can say that 2 raised to 44 is congruent to 1 modulo 89. Okay, means what? 89 divides the difference of these two numbers. 89 divides 2 raised to 44 minus 1. This proves that 89 divides 2 raised to 44 minus 1. Example 5. Prove that 2 raised to 340 is congruent to 1 modulo 31. Again this is very bigger number, so you have to be careful. Just as like previous problem, you have to take the powers of 2 and their congruence modulo 31. As like we have 2 is congruent to 2 modulo 31, 2 raised to 2 is congruent to 4 modulo 31, 2 raised to 3 is congruent to 8, 2 raised to 3 is 8, congruent to 8 modulo 31, 2 raised to 4 is 16, congruent to 16 modulo 31, 2 raised to 5 is 32. But 32 is greater than 31, so subtract 31 from 32 and it will get 1. So 32 is congruent to 1 modulo 31. Indirectly 2 raised to 5 is congruent to 1 modulo 31. But this 340 is divisible by 5, means it is a multiple of 5. It can be written as multiple of 5. So how can we write? It is 68 into 5. This 340 is 68 into 5. So this 2 raised to 34 can be written as power of 2 raised to 5. Like this, 2 raised to 340 is equal to 2 raised to 5 raised to 68. Okay, but this 2 raised to 5 itself is congruent to 1 modulo 31. So it will be congruent to 1 raised to 68 modulo 31. 1 raised to 68 is 1. So indirectly it is congruent to 1 modulo 31. And in this way we have proved that 2 raised to 34 is congruent to 1 modulo 31. Thank you.